Hey, welcome to the stream. Today I'm going to be working on my line number programmer, or my line number program for the DWARF debugging system. So we're working on parsing the line number information, and I'm hitting up a bug. Hey, how you doing, Vimpol? Thanks for jumping on. So yeah, I'm hitting a bug in my line number program where it hits this invalid program, and that's because the line state is at 66 and it has this delta of minus 71, which shouldn't happen. Line number program should never go below 0. And so we have this invalid standard opcode that's happening. And so what I built out last stream was this debugger for the line number program information. And it lets us parse through the data. This is all the binary data that we have for the line number program. And gives us the state, so we can kind of walk through the state. So that's what I'm doing right now. I've got it so you can set, I set a little breakpoint for just about all around here, which starts at the last time that the state is reset. So then I can walk through and see why the state's getting off. So right now I'll just start over here. Continue. Oh, I need to fix something so we can scroll down faster. But for now, we'll just do the slow scroll. It's gonna be a minute. You can see all these different sections though are different line number program sections. They're usually split up by this buffering. It's a Zig addition to things. You can see that. Got the double A's in Zig. Double A is typically a undefined value, so that's why I've got it highlighted red, though in those cases those might just be normal. So when you see a run of double A's. All right, 4948 is where we're going to. So offset 4948. There we are. Put that near the top. So here we are in sequence. So if we go to the next one, we get the padding. There should be 23 bytes of padding, X17. So 1, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7. Should put us right here. And yep, puts us here, which is a non-standard, or it's an extended opcode 0. The length of this opcode is 9. The opcode is 2, which is set address, which is almost always the first opcode in a new run or a new sequence for the line number program. So it's going to set the address, which you can see here. The address is right here. This is in Little Indian, so A0, E1, 0301, 0301, bunch of zeros. Okay, next one, set file. And then the file is going to be 2D. Yep. And then set the column. Column should be 3C. And we're going to advance the line. The line's currently at 1 to 303. Oh no, advance the line to EF. So that should put us at F0, right? No, 70. E, F, F. That shouldn't. Okay, see, this might be a mess up. Oh, no, okay. This is where I need to pull out the old documentation. So let's see, tab gets in 6.2. line number program. So this is a LNS. So this is a standard opcode. So standard opcode, advanced line. Special opcodes. Here, standard opcode. Advanced line. The LNS line opcode takes a single signed leb 128 operand. Okay. So the signed leb operand is 0F00. We're going to write that out. That's going to be C. E is 1, 1, 1, 0, and F is all ones. So that be 1 is the extend. Okay, so it's 1, 1, 0. It's gonna be 0, 1, 1, 0. Okay, so whatever number 1, 1, 0. Yeah, 1, 1, 0, 1, 1, 1, 1, 1, 1, which should hit 7 when you add it to 1, right? So let's do this. Let's do the hex calculator. You know what? We'll just pull up binary. We'll just do this. Zero B Z 0, 1, 1, 1. No, 1, 1. So E is 1, 1, 1, 0, but this one is actually 0, 0, 1, 1, 0, 1, 1, 1, 1. Okay, 111 by X. This. Yep, okay. So the math, it all checks out because there we go. That line up is going to be 70. We're going to copy. Copy doesn't change the registers at all. Now we're going to set prolog end. So that should set this to where's prolog end? This should become true. Okay. Now we're going to set the column to 23. Okay, then we're going to advance the line, this time by 13. 83. Const add program counter. Yeah, thanks. This is obviously not the actual debugger, but it's the debugger for the debugger, and I'm quite happy with it. I used, I think it's Rocker Rager's libvaxis. Let's see. Is that who wrote it? Libvaxis. Yeah, Rocker Rager wrote it. So very good. Very nice program. Made it really simple to write. Just a quick TUI tool for this. Okay, const add program counter. This is another one. This is number 8. Let's see, line program takes no operands. It advances the address and op index registers by the increments corresponding to special opcode 255. So it advances address and op index. Okay, well, I'm interested to see what happens there. Okay, so it just fully moves this. And then we're going to get a special opcode of 228. Once again, advancing the address. Now we're going to advance the program counter here, and it takes an unsigned LEB 128 operand. So 8601. This should be it right here, because 86 is 1, 0, 0. Yeah, 1, 0, 0, 0, 1, 1, 0, 0. So then, yeah, so this should be these 2 bytes taken, yeah, and it just advances the program counter. which I think it just moves the address. Yeah. I think op index is almost always 0 in this file. So every program counter just moves address. Op index, I think, is something that's used by other architectures, not x86, but I could be wrong. Okay, we're just going to copy, then we're going to set the column again. So really, we're interested in things that modify the lines, not this. This won't, this won't. Add PC, special, set column. Advanced PC. Now I do know the address that's going to be bad. It's going to be right. Let's see, unit length, current offset 4A97. So when we get down to here, 4A90, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, right there. So this is the one that's apparently bad. So we'll get down there. It's a column, advanced program counter. It's a column, a program counter. Columns getting just moved around all over. The line number's not changing, which is odd. Set file. This will definitely change the line number for sure. Not this one, but the next one should change the line number. Yep, advanced line. And here we have BD7F. I think that's a negative number. BD7F would be, let's do this. Bin X0X BD7F. Oh, it's a little Indian. 7F BD. So we have 1 0 1 1 1 1. So yeah, so then BD 1 0 1 1 1 1. Okay, so then we want V7 here. And then these are all just sign extensions, so it is negative. It's negative, whatever this value is. Let's see, 0, B, yeah. So this can be a negative number. 83. Zero one 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 0 1. See. Want enter binary at 8-bit. One, two, three. Yep, just tell me what the dang number is. Negative 67. Okay. And so minus 67. $43. So this should take us down to 40. X 40. Yep, there you go. Okay, 5, 3, 1. Set file advanced line. Okay, C3, 0, 0. So this is advancing quite a bit. What is C3? Now I gotta should probably add something that just calculates all this for me. So C3 is 0B 0 0 B 1. See, C is 10A B C. There you go. 0 0 1 0 or 1 1. Okay. 67. Okay. 43. So we're going to go back to 83. No, 53. Okay, okay. That's wrong. It only added 13. Oh, okay, let's take a look at our code for let's see. It's slab read slab 128. Go to the definition. Okay, let's test out this one. Try test read slab x03 no c3 C300, and this should be I said 643. Well, hex 43, not hex 13. Definitely shouldn't be 13. Hex 13 would be like, there's no way that's just wrong. Whatever's doing is wrong there. Okay. Zig build test, please. Okay, that works. So I'm right. I do, just to make sure. Yeah. Okay. So this is right. But where on earth is it getting its idea that this should be 43 or 13? Because was that 40? Added hex 40 or hex 13 was added to it. Let's take a look at parser here. Const data advanced line. Read sleb. Print log.debug. Delta is res. And RG13. Let's see. Okay. Before we move this, I do want to add a thing that when we event handler when we do the continue to breakpoint, I want to reset the offset to be nearest multiple of 16. So we take breakpoint equals new offset should be just to make sure. This is a bit of spaghetti here. So let's see, we go through, we read in, we take the line number offset, which is offset to the line number program. That should be 0, and then the breakpoint is how far into that program we want to go. So that should be fine. We just need to add offset. Okay. So we just need to do this. App.data. The data, no, it's bytes model. Bytes dot offset should equal I think it does need to be a multiple of 16. Offset equals min of bytes model offset plus 16 or bytes length. So we're always adding 16 to it. So let's what we want to do is basically floor div. Is that what it is? BP. We don't want it to be PEP. We want it to be, come on, floor, div floor. Div floor BP 16 times 16. Okay. That should work. So if we jump through this, Continue. Oh, it didn't work. Why didn't that work? Oh, because this didn't compile right. Okay. Expected type U32. Found U size. There we go. Perfect. That worked. Okay. Next stop. We were down here, so we just need to get down to here. Set file. Up down to 40. Okay. Oh, the line got dropped down to 10. When did that happen? I wasn't paying attention. Is that here? Red. Because that would make sense then why it would be there. Let's out.txt. Yep. Let's walk through that again because I might have seen it. 83. $40. And then advances the line again. This time, yeah, it is 50. 50 is 5 Python 0b 0 1 1 0. Oh, no, 1001. That's right. Okay. 000. And so that is continuation byte. And you guys 0Y. Okay. $72. $90. 5001. Let's see what that is. Slab. Yeah, here it is. Five zero zero one. I should get an error. Tell me what you expected and found. Expected 67 pound minus 48. Why is it a negative number? Oh, because it's a sign. It's signed. Yeah. Okay. Yeah, it's signed. So then I have to like, okay. Might as well keep it here. $30. Okay, so yeah, it does drop to 10. Or hex, 16, line number 16. But yeah. Dang, okay, so that works. We set the line again. Set the column. Now we set the line again. I'm not gonna lie, this doesn't make sense. We keep changing the line in the column back and forth. So now we're up to 53. 3 zeros, just adding that. The special line number. Now we're advancing the line again. This one's 2F. So 8-3 plus 2F is going to be B2. Okay. Okay, we're going to advance it again. This time we're subtracting. We already decided that that's minus. We drop 48. No, 30. Yeah, so should take us down 3. That would take us at 9-2, 8-2. Oh, B's 11. Yes, B's 11. So yeah, 9-2. Advanced program counter. Advancing the line. This is going to be 51. Oh, wait. That's wrong, right? No way that 5-0, okay. These should not be the same. These two should not have the same result. So there's something wrong with the way I'm reading SLabs. And I guarantee that's why my math is wrong, or my number program is probably not working. Okay, I don't guarantee it, but there's no way that these can be the same number. So that would be ridiculous. So let's go to the definition of slab here. Variable length data. Yes. And this example leaves much to be desired, but the encoding for signed 2 complements LEB 128 numbers is similar. So let's start here. Integers may be encoded using Little Indian base 128 leb 128 numbers. Leb 128 is the scheme for encoding integers densely that exploits the assumption that most integers are small in magnitude. This encoding is equally suitable whether the target machine architecture data is big Indian or little Indian. It is little Indian only in the sense that it avoids using space to represent the big end of an unsigned integer when the big end is all zeros or sign extension bits. Unsigned little Indian 128 numbers are encoded as follows. Start at the low order end of an unsigned integer and chop it into 7-bit chunks. Place each chunk in the lower order 7 bits of a byte. Typically, several of the high order bytes will be 0. Discard them. Emit the remaining bytes in a stream, starting with the low order bytes. Set the high order bit on each byte except the last emitted byte. The high bit of 0 on the last byte indicates to the decoder that it was encountered the last byte. The integer 0 is a special case consisting of a single 0 byte. Table 7.7 gives some examples of unsigned LEB 128 numbers. The 0x80 in each case is the high order bit of the byte, indicating that an additional byte follows. The encoding for signed 2's complement LEB 128's SLabs numbers is similar, except that the criterion for discarding high order bytes is not whether they are 0, but whether they are consist entirely of sign extension bits. So the criteria for discarding high order bytes is not whether they are 0, but whether they consist entirely of sign extension bits. Consider the 4-byte integer -2. Let's consider it. Then, oh, don't. Python. Come on. Come on. Need a true two's complement calculator. I don't really like this one. Two's complement decimals. First, we take the 2. Write down the binary number. Yeah, I know what 1's complement is. Convert all the values. Take 2's complement by adding 1 to the previous binary number 1. Okay. Yep, that's this binary number. Makes sense. Okay. The three high-level bytes of the number. Oh, consider the 4-byte integer -2. The 3 high-level bytes of the containing number are sign extension. Thus, leb would represent it as a single byte containing the low order 7 bits. To be 1 1 1 1 1 1 0. With the high order bit cleared to indicate that the end of the byte stream. Note that there is nothing within the leb 128 representation that indicates whether an encoded number is signed or unsigned. The decoder must know that the type of number to expect. Table 7.7 gives some examples of an unsigned LEB 128 number. And table 7.8 gives some examples of signed LEB 128 numbers. Okay. So here's our examples. I'm pretty sure that there used to be. Okay. So 2, first byte is 2, second byte 0. So let's take a look at our friend here. Yep, our friend here, Mr. These two numbers. We have, let's write this in Little Indian just to make it easier. So 0, I can't, I think in Big Indian. 0, so 5 is 1 0 0 1. 0 0 0 0. Then we get, what is it after that? 1 0 0 0 0 0 0 0 1. Okay. Maybe we should do this in Little Indian style. Oh no, Big Indian. I was mixing up my Big Indian and my Little Indians. There we go. B. Now this is a sign extension bit saying, or not a sign extension, this is saying this is extended. So this should no way be -48. Not at all. Zig build test. essentially what we're doing is we're getting a 1. If this was negative, these would be all 1s. In that case, we just have all these be 1s. Basically, this would be 1 at least, and then am I wrong? Crazy? Okay, so what we basically get is this number. So this should be 72. Oh. What happened to my Bork? Okay. Okay, so it should be 72. Oh, it should be, keep missing that 0. 244. And to prove it, let's get what negative 48 is in 2's complement. Put decimal in, 48. 2's complement 48 is 10110100. Copy. And I'd like to get the hex value out. Calculate, please. Okay. Try, test, read, sleb. Oh no. So then this would be, broke this up into 7s. These are all sign extension bits. So we don't need this byte here. Just need this. Makes sense. So this would be 0, 1, 0, 1, 0, 1, 0, 0, 0, 0. Off. Off. Off, off. That is 50. 50, hex 50. No, it's not. No, it's not. Yes, it is. 1, 2, 4. I was off. My putting the bit in the wrong spot because I'm a moron. All right, so that is hex 50. Okay. So, but then it shouldn't be reading this 1. That's why. That's why these are both 48, because these ones, these aren't read. Arg, why is it? Okay. Did I just go down that path for no reason? Okay, here we are. BD, we've determined BD7F should be minus 43. Let's just add that to this R. Okay. Let's do 0x30. I don't read. I haven't been using the standard leb because I want to use it with the reader, and standard leb doesn't work with that. And then I just have some different requirements. I need to know how many bytes were consumed, and you just don't get that with the standard leb. So that's why I don't reuse it. For some reason my Borg is out. Borg reconnect. Borg. Borg start. Oh yeah, I got disconnected. That is why. Copy. Let me It's just not working today. It's just too bad. I'll just keep an eye on chat over here for now. Until I can figure out why Bork isn't working. Okay. X48 is 30. Yep, we decided that. Okay. Okay. So BD7F. Here it is, advanced line. Oh, idiot. So it wasn't continuing. Why did I think it was including the one? C300. Counting writer, yeah. In 330. Yep, okay, that works. Okay, so I keep messing up in this. Let's see. Advanced line 2F05. 2F, okay. Advanced line 50. Okay. We're at 82. Which is right, because yeah, we subtracted 3. Okay. This is where we were before. Okay. I went on that detour again. Set the column. File. So here's a line 5.1. So now that we've learned about this, 5.1, 0B, 0.1, 0.1, 0.0, 0.1 should be yeah, 30. I put in a binary 8-bit number. 110 1101 0001 minus 47. X7 2F. Not surprising. Okay. To F. To F. (8.2) minus 2F. I don't want to do that math. It's too hard. That's too hard hex math for me. Hex 0x 8.2 minus 0x 2F. 53. There we go. Now we're going to advance the column again, 31. So that would be, put us at 8.4. Why do we keep jumping around these lines? Okay, and I guess that makes sense. That's kind of how programs work. One. See, setting column, special, setting the column again, advancing the program counter, something special, setting the column again, advancing the program counter, something special, setting the column again, advance the program counter, something special, setting column, advance program, special, set column, special. Okay, advanced line 4A. Okay, so 1 0 0 0 1 0 0 1010. This is a negative number. Yes. Negative what? I need to work on my two's complement intuition, but right. 0 1 0 1 0 1 0 0 1 0 0. Whatever that is. One 1 0 0 1 0 1 0 minus 54. Okay. So we subtract 36 from here. So that would put us at 4 minus 6, put us at the borrow 1 8 7 14 borrow 16, so 20. I don't know. I can't borrow x 80 minus 4e. Okay, that sounds reasonable. Fred, was that the right? Did I mess up there? Ugh, I jumped. That's okay, I jumped. BD7F. I think I've done BD7F. Yeah, minus 43. Okay. Okay, that checks out. I just skipped a line. Okay. I think this is all correct. Advancing a line. 4 6. So we're gonna drop a bunch. How much? See, 4 and 6 is gonna be 0 1 0. Negative 58. Eight, 3a. Okay. They'll clue it. That'd be hex 4 1. Seven. Okay. Let's see if that's correct. Yep. Not really surprised. And then we're going to advance the line. This time C3 0 0. It's a positive number. 1 1 0 0 0 0. Okay. 3. So that's going to be adding 0 0 b 1 1 0 0. Let's see. then 0011 195. Next step. All right, so we'll get to CA. All right. For A. Yep, that's right. Okay. Then we do another advanced line, getting closer to where it breaks. And sorry, advancing our line is 3A. 3A should just be straight what we're advancing. So now we're going to take it from 4A to 3A, which is A and A. 4A. Four, okay. Back to 8-4. I mean, what's the target? A97. A9 7 0 1 2 3 4 5 6 7. So B9 7F. Yeah, this value here. Oh, B9 7F. That's different. Okay. 2F is going to be 6 plus F leaves us at 5. Carry the 1. 3 puts us at 9AB. So B5, B3. That is 6 and F. All right, that's interesting. B3 is not the right answer there. Or A50. Let's do this again. But we're gonna jump straight to here. Wait. It was totally I was looking, oh my goodness. Was I looking in the wrong spot? I was looking in the wrong spot. Yeah. Okay. That makes sense. Okay. 4, 6. So this is a negative number again. We're going to subtract a whole bunch. Okay, here we are again. 5, 1. This is again negative number. And think we already know what that one is. We got it down here. 512F. Ooh. Oh, keep looking at the file number. Okay, yeah, 2F. Okay. Should be like 7 minus 2 is 5, so it should be 4. And then 16 plus 9 minus F. So 16. 9 minus 16 is okay. Yeah, 40. 4A. Yep, that's right. 3B, A and B gets you 10 plus 11 is 21. That takes you to 5. 8, 5. Yes. Okay. 5, 0, 2, 3, 0, 5. Okay. Here we are. 85 BD7F, which we already know. BD7F is minus 43. So 85 minus 43 is getting us to 42. Yeah, B9 7F is going to be a big number. B9 7F is 0B. 7F is 0, 1, 1, 1, 1, 1, 1. Rid of that number. And then B9 is 0. We're losing that 0. We're going to go 1. 0, 1. No, 1, 1, 0. 1, 1, 1. And 9 is 1, 0, 0, 1. Minus 7. That can't be right. B9 7F. Right? Because that's not the most efficient way to store. B9. Let's do this. Then B9 Oh, okay. I missed a 0 there. Okay. Copy that. 5, 6, 7. Wait. 1, 2, 3, 4, 5, 6, 7. This is just a sign extension. 1, 2, 3, 4, 5, 6. 5, 6, 7. Okay, so it says it's negative. 0, 1. Okay. That's okay. Calculate that. Negative 71. Or 7. So it's just off by 5. Boom. Yep. And it crashes. It's not surprising. Question is why? There we go. Okay, why does it crash? Why is it not? Take the shifts and the adds right. I think I need better visual of this. What's going on? Speed this up when we've got, I think, yeah, I want to do this. Standard. Const standard equals struct code, and pretty sure the standard ops all just take one operands or less. None of them take more than one operand. So let's take a look at that. Line number information. Special opcodes. Okay, standard opcode takes no operands, single operand, single, no operands, no operands, no operands, single, none, none, unsigned. Okay. when we get this standard op, need to switch the opcode to opcode. And advanced PC. This is all messing with state. Get next opcode. Needs to take the byte. If the opcode is special, you get the opcode. If the opcode equals 0, we get this one. If the opcode is less than 12, then we return standard equals opcode and dot operand equals, we'll just do null right now. Excuse me, sneeze. Oh man, allergies. No member function name format number for standard opcode. Doesn't like. Oh yeah. Standard doesn't have a format number value because where is it trying to format that number? Here. It's right here. Try standard advanced standard opcode. So debug opcode LNS T. It's T. We need to do lines opcode opcode. Wait. That's wrong. Right, yeah, here. Format, yeah, standard. Step standard expects a stat. We gotta do change this to expect a okay. Okay. So what we need to do is instead of reading it here, we will have already read the parameter and in the step function. Let's add that here. What we want to do is instead of reading the parameters here, yes, only in the step function. Up advance would be up code.operand opcode.operand opcode.operand operand opcode.operand here. We're going to do that. To get next opcode, what we need to do is take the reader. We got to read the next parameter for all these. I don't like this. No, that's not the right way to do this. Okay. That's going to be the right way to figure out why. I'm off by 2. This is weird. Yes, I want to take a look at this. What's up with this? It's a whole bunch of special Why are we just adding 32 to the address? A bunch of times. Does it make any sense? We're going to print off. We have header information. I want to see some of that header information in here. Bytes, no. Data model. Okay, fields and 1, 2, 2. Okay, children 1 equals, or children 0. We're gonna put this at the top equals. Let's see. We need to make a text thing. Header text equals standard.format.alloc print. Version. All right. Data.header.version. The letter in there. Equals. We need to add in text view. Use equals. Text view 0 equals that. Let's see. Equal. I just say okay. Weird. Well, I've got to close up for today. Thanks for watching the stream. Hopefully I can figure this out. I'm going to try to keep working this off stream so the next time it's a little more interesting. Thanks for watching. I'll see you later.